Okay, let's look some more at the 23-10 field manual and explore what they have to say about humidity and its effects on trajectory. This is another thing that's very misunderstood in the long-range shooting world, and hopefully this video can get this straightened out real quick. So let's just go straight to the section on humidity in our 2310 and read what they have to say here real quick. Okay, so humidity. Humidity varies along with the altitude and temperature. Figure 3-19 considers the changes in altitude. Problems can occur if extreme humidity changes exist in the area of operations. Now that part is true, problems can occur, but it's not going to be really due to the reasons they're saying. Let's read on a little bit. That is, when humidity goes up, impact goes down. When humidity goes down, impact goes up. That's actually completely wrong. Now, intuition would tell you, if you're just thinking about it, well, if you got more humidity, that seems like it should make the air more thick, right? So if the air is more thick with more humidity, then your impact should go down because your bullet's slowing down faster, right? It has to cut through all that humidity. Well, that's not actually how it works. It is true that if you have liquid water, that's going to be a lot more resistance than just air, okay? So if you have a glass of water or just liquid form H2O sitting in the glass, that's going to be a lot more resistance than air would give you on a bullet. But when you have water vapor, you're talking about something completely different. Water in its gas form, water vapor, is actually less dense than the normal atmosphere. And if that don't seem to make very much sense, let's kind of go through this real quick. We'll go through a chemistry refresher for you guys. I don't know if you remember way back, maybe from high school again, Avogadro's law in chemistry class. If you remember that, you're going to know that you're going to have a constant amount of molecules present per unit volume for any gas at a given temperature and pressure. So let's compare the molecular makeup of the normal atmosphere that's just surrounding us right now, okay? And then we can compare that to water vapor, and then you'll see what I'm talking about. So first thing you got to consider is that basically your atmosphere is composed of lots of different elements in their gas form, right? And those different gases have different atomic weights to them, so they have different weight to them, and that's going to kind of determine our density. So, for example, if you had pure hydrogen gas, for example, that's really low on the periodic table. That's only got a molecular mass of like 2. So that's going to be a lot less dense than if you just had pure neon gas, which would have like a molecular mass of 20 or something like that, right? So there's a difference in density between different gases. The higher you go up on the periodic table, the more heavy that gas is going to be per, volume or whatever. So let's look at the normal air that we breathe now. And the atmosphere around us is composed of mostly nitrogen, about 78% nitrogen. And if you want to figure out the molecular mass of nitrogen gas, you got to consider that these aren't molecules that exist just all by themselves in nature. They're going to be usually diatomic, which means there's 2 of them hooked together. So like a nitrogen gas molecule is going to consist of 2 nitrogens. And so your molecular mass for nitrogen gas will be actually 28. And same thing with oxygen. There's 20% oxygen in the atmosphere, or about 21% oxygen. And the molecular mass is, again, it's going to be O2. There's going to be 2 oxygen molecules. So your molecular mass of oxygen gas, O2, will be 32. So we can simply just go through, and here I'll show you, I'll write this down for you so you can see what I'm talking about. You can look at the different volumes of the air, put that in one column. We'll have oxygen, about 21% oxygen, 78% nitrogen, and then carbon dioxide is a real tiny amount. It's less than 1% for all the other gases basically put together, okay? And then we can go over here and figure out the molecular mass of these different gases, okay? Let's write those down. Oxygen is going to be 32, nitrogen is going to be 28, carbon dioxide is going to be 44, and then hydrogen is going to be 2, and then some of these other gases are a little heavier, but they're in such small amount it's not going to really add up to anything. then you can figure out your actual molecular mass in the air, okay? And you just basically multiply. So the total molecular mass of the portion of the air that's oxygen is going to be 20% of 32 kilograms per mole of the molecular mass of oxygen. So that's like 6.704. And then we have our nitrogen. That was 78% of 28.02. That gives us molecular mass of 21.88. And then we have our carbon dioxide, and we'll put that in there just because that's like 0.03% times 44. Even though it's a heavier gas, there's so tiny amount of it, it's only going to give us a molecular mass of 0.013. And we'll just go through the rest of them here real quick. Okay, and then all we have to do is simply total these up over here in the column, and we have a total molecular mass of air, the normal air that we breathe, of about 28.97. So that's the mass of air. Now let's do the same thing for water vapor, okay? Now if you take water vapor, water consists of H2O, right? You got one oxygen and two hydrogens. So you're going to take your one oxygen and you're going to basically add on your two hydrogens here. And this is quite simple because it's just a pure water vapor. And when you figure this all out, your molecular mass of water vapor is going to be 18 grams per mole, okay? So that's considerably less than the molecular mass of dry air, which is 29 grams per mole. So what really did it was the hydrogens. You got most of the space being used in these molecules. You got an oxygen, which is, right around the same molecular mass as nitrogen, just a tad bit more. But you do have the two hydrogens in there, which are really, really light. So it's the hydrogens that throw it off. So water vapor in its gas form is way less dense than dry air. So actually, if you have 100% humidity mixed in with your normal air, your air density is going to actually get lower. So on a day where there's a 0% humidity, no humidity in the air will be actually more dense because there's less water taking it up. And as we just seen, water's density is 18 grams per mole for water vapor. And the regular air is, 29. So the more moisture you have in the air in gas form, you're going to have basically less dense air. So it's kind of counterintuitive how that works, but when you actually figure it out chemistry-wise, and atmospheric scientists are very well aware of this, meteorologists know all about this, but in shooting circles, and if you read long-range, hunting articles, or you'll hear this 23-10 field manual, what they say about humidity, you'll hear that being repeated all the time, and it's actually incorrect. And some of the reloading manuals, I believe, has this incorrect as well. So it's kind of interesting. It seems like water vapor should make the air more thick, but it's the opposite. So we can see by how much in just a little bit here. So let's take a look at what the 23-10 continues to say here. So we just determined that is when the humidity goes up, impact goes down. That's wrong. It's the opposite. When humidity goes down, impact goes up. That's wrong. Okay, so that part is completely wrong. Let's read on. Since impact is affected by humidity, which the impact will be affected by humidity, that is true, a 20% change in humidity, oh, here we go, another rule again like we had with temperature, okay? A 20% change in humidity equals about 1 minute as a rule of thumb. Keeping a good sniper data book during training and acquiring experience are the best teachers. Okay, that's their way of weaseling out of their inaccurate stuff here, I guess. So that last part's true. You better keep a good sniper data book because this 20% rule is really going to throw you off. You're going to be hitting in the wrong direction, so that's not going to help you. So let's take a look at how this is actually going to affect an actual trajectory in real life, okay? So let's get out my range cards like we had last time. Okay, so here's the same load we had last time, which was our 308 Winchester, the 168 grain bullet and all that. We're going to keep everything constant. And our variable that we're changing is going to be our humidity. So our barometric pressure and our temperature and the muzzle velocity is all going to be the same for the purpose of this little experiment here. So on the far left side, we have the 0% humidity. And this will be our standard conditions, so-called. So this is the actual point of impacts listed in the elevation here. At 1,000 meters, the bullet strike will be 50.6 minutes of angle, okay? So that's our actual strike. That was confirmed, okay? So the suggested correction, if we had a 20% increase in humidity, according to the 23-10, would be to add 1 full minute of angle. So it's telling us to add a minute of angle, which is wrong, right? Because actually, if you have an increase in humidity in real life, your air density is going to go down. So your bullet's going to be going faster, which means it's going to drop less. So you need to apply less elevation to your firing solution. But let's just pretend like we went along with it. And we took the advice of the 23-10 and, okay, let's dial in our 1 minute of angle. We're going to crank it up to 51.6. So how much should we have cranked the scope by, and in which direction? Well, as we just talked about, you're going to actually go in the opposite direction because the field manual has that backwards. So we're going to be applying less elevation because the air is actually getting thinner with higher humidity, which is counterintuitive, but that's just the way it is chemistry-wise. So let's look at it. And in reality, with the 20% increase, and we can look at this middle card, this is showing us where our actual impact is going to be with the 20% increase in humidity. And you might be surprised, it's a very tiny amount of shift, okay? So at 1,000 meters, it only moved us like 0.1 minutes of angle. That's going to be like almost an inch. So the 23-10 field manual was telling us that it would be a full minute of shift for a 20% humidity change. In reality, it was only a tenth that much, and it was in the opposite direction they said. So as you can see, the field manual's just kind of way off here. And you might be wondering, well, how come it's so small of amount for that much of a humidity change? You'd think 20% would be a significant amount. Well, let's look at 100%. Let's say, okay, we have 100% humidity. All the other conditions are staying the same, but now at 1,000 meters, your point of impact is still 50.3. So your actual change from the standard conditions from 0% to 100%, the change in elevation setting was only 0.3 of a minute. That's just one click. That's like 1/4 minute of angle at 1,000 meters. That's only like 3 inches or something. With the full swing, that's 100% humidity. So as you can see here, and we're going to basically do a blanket rule for ourselves, is inside 1,000 meters, the blanket rule for humidity is don't even worry about it. It's going to adjust it. The difference between 0% humidity and 100% humidity within 1,000 meters is so small. And I mean, unless you want to hit like a beer can or something like that at 1,000, then you might have to adjust, like a 1/4 minute or, just hold under just a little bit. So you do want to be aware of that if you're making a shot on a real tiny target, because it will change it a little bit. But usually you're not going to have that small of a target to worry about. So as you can see, the US 23-10 was incorrect in this as well. And that's probably why they added that last sentence in there. What did they say? They said basically keeping a good sniper data book during training and acquiring experience are the best teachers. I think that whoever was editing this book, they probably had an argument with some guy who was supposed to be the scientist, and then the other guy was like, well, no, that doesn't seem to be what matches reality. So they probably argued, and then they argued that sentence into there kind of as a, so the one guy would be happy or whatever, because he's like, that's not the way it works. So it's just kind of funny to read that. I'm wondering what the story is behind that. But that's my suspicion anyways. Now, if you're shooting at extreme ranges, if you're shooting 2,000 meters with one of these BMGs or a 408 Shytac, or if you're shooting at a mile with one of these bigger calibers. Humidity, if you do have an extreme change in humidity, like 100% change, let's say your standard conditions were like 0% or whatever, and that's what all your ballistic tables are calibrated for, and you're at 2,000 meters or 2,700 meters, you're shooting really, really far, then it will shift, 100% increase in humidity will shift your point of impact. But beware that it is in the opposite direction from what this particular field manual tells you. Now, I believe it is the Sierra reloading manual and their discussion about humidity that actually gets this correct. So there are those sources out there that are right on this, but the general rule of thumb that's been applied across most of the long-range shooting world is actually dead wrong. So that's something you definitely want to be aware of. And for most purposes, humidity is not anything you have to even really worry about. And if you may be wondering why is it so little of a change, because there is a significant difference between the molecular mass of water, which is 18, and dry air, which is 29. It seems like, well, that's almost twice as much. So it seems like there should be a bigger difference, but you got to consider the fact that air, even completely saturated with as much water vapor as it can hold, and that depends on temperature as well. Cold air and hot air are going to be able to hold a different amount of moisture, so that's a whole nother dynamic to this. But thankfully, if you consider how much moisture is actually in completely, saturated air, like 100% humidity, it's not going to be, the air is not 100% water vapor. It's just a very small amount of the air is that. And if you look at this humidity changes charts I was showing you, at the very bottom, it might be kind of small for you to read, but it has the actual atmospheric density, and that's factoring in all the factors, temperature and humidity and everything. And with the 0% humidity at the 60 degrees Fahrenheit, your atmospheric density is 0.07541 pounds per cubic foot. And if you go all the way up to 100, the change is only just a little bit, because you got 0.07490 pounds per cubic foot. So it's just a small amount that it actually has changed, because, again, even air that's saturated with what they call 100% humidity, obviously the air isn't 100% water, or you would basically die, right? So it's not that big of a difference from 0 to 100% as far as air density changes actually goes. So unless you're shooting like extreme ranges beyond 1,500 or 2,000 meters, and you're shooting at a relatively small target, you don't need to even worry about humidity changes. So that's actually something that you can pretty much just forget about. As we've seen before, the difference between 0% humidity and 100% humidity at 1,000 meters for the 308 Winchester load we were talking about was only like 0.3 minutes of angle, which would be like, under 3 inches or something like that. So it's a very tiny change with 100% difference. Okay, that was our video on humidity. Again, when we show you how to put together our super detailed ballistics tables, we will show you how to factor in humidity for extreme range shots, if that's something you do want to adjust for. So we will cover how to do that. But again, the concept is the most important thing, and it's not at the top of your list of priorities when you're doing a firing solution for anything inside, any normal range. Okay, our next video will be about barometric pressure. And then after that, hopefully I'll remember to do a crash course on wind, and also angle of fire corrections. And that will basically conclude our part of the series titled Basic External Ballistics. After that, we will move on to our advanced ballistics portion, and we will get into a lot of detail. We'll start out with internal ballistics, advanced internal, all the different factors that influence muzzle velocity. And then we'll have a brief discussion again on intermediate ballistics, and then we'll move on to advanced external ballistics. A lot of you guys are curious about the Coriolis and spin drift. And after all that, we should be pretty well equipped to go ahead and start setting up our ballistics tables. And I'll show you exactly how to custom tailor those to your particular weapon system. And then you'll be able to nail that mule deer buck at 1,000 yards without too much difficulty, hopefully, after you get all your zeros confirmed and everything squared away. So stick around for the next one. Barometric pressures next.
$890. Confirm.
Green light.
It's a hit. 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 Nailed it. Yep.
Okay, 1.13 kilometers.
Oh, you got it!
Oh.
Holy cow, you got it!
Indexing 20.36. 20 point. We're going 20.4. Oh, yeah. Good call.